Chennai. So I am also a part of Mars Rover team and then Technocrats team in Vellore Institute of Technology, Chennai. And also I am taking care of placement. That's the thing. Okay, and so just my presentation will be introduction to robotics. Just now we have come across a very good lecture on recent trends in robotics, but I want to touch some basics about robotics. Then we will move slowly to introduction to manipulator and then kinematic analysis. If time permits, I will discuss some of the activities whatever happening in VAT among the private engineering institution by MHRD India. That's the thing I want to convey. And then, as like our professor said, just a few minutes I will take. Is it okay, or shall I skip the introduction, professor, so that we can move to kinematics?
No, sir. You please continue.
Okay, fine then. So, as like our earlier professor said, robotics is a. So, if I want to design any one of the robot, then I should have a strong fundamental knowledge on robot design. And when it comes to design, means I should have some mathematical knowledge in that will help me to do kinematics and dynamics related work. And then after making the calculations and then rough work in the background of mechanical engineering, then I should know how to make this one to work by using electrical and electronic systems. So once I am making to actuate the robot by using the electrical and electronics, further I want to make it to work by its own, otherwise more easily, just like a command I want the robot to move. So at that time I need computer science. So if I am calling myself as a robotics engineer, means then I should have some knowledge on all these aspects. Then only we can call ourselves as a robotics engineers. Okay, that's the thing. So that's only we are calling this one as a robotics is a multidisciplinary field. If suppose you are interested in robotics, but if you are unable to do all these activities, means you can have a collaborative work. That's only, even the earlier professor said it's a collaborative field. Next one, most of them, they will get confused with automation and robotics. So just I want to brief about that. So automation means it's a machinery designed to carry out a specific task. That is the thing, automation. But if your robot, means it's a machinery designed to carry out a variety of tasks. So that is the major difference between robotics and automation. And next one is robot history. I think you know very well about this one, but just I want to brief. It started in 1920. So it's not a new one, okay. And then they started making an intelligent mechanics device. Okay, past 100 years, we are doing the same thing. And so only in the earlier days, you can see so many automatic toys and mechanisms they have done in the movies also, and some of the novels also they used to portray. And the robot came from, you know, everyone. Then it's a Czech writer, Karel Čapek, in the play called Rossum's Universal Robot only introduced. And then the plot is very simple. This particular book, if you are getting, please read it. It will be very nice. So the plot was very simple. The man makes robot, then the robot kills man. So that's really what happened is in the earlier movies. If you see that Terminator 1 and all, the robot will kill humans. That's the thing. So later on, they realized that the robot can be used for a good purpose. So in Terminator 2, so they made both the robots as one is hero and another one is a villain, like that. Okay. So the robot coined by Karel Čapek in 1921. And next one, this is the fellow who is made the three principles of robotics, or we can call it as a law. And because of him only, we are making all these robots in particular aspects, like the robot should not injure a human being. That is the first law. Second one is the robot must obey the orders of the human, but it should not conflict the first law. The third one is a robot must protect its own existence. Okay, till now I think we are solved the first one. Robot may not injure a human being. I think we have developed the robots in that particular law around 90%. Law 2, the robot must obey the orders given it by. That is also we have made up to 90%. The last one, still we did not make the robot in that category. That is, the robot must protect its own existence. Okay. So definition, general definition. So it's, even though it is a very old one, 1920. but the definition came on 1979 by Robot Institute of America. That is, a robot is a reprogrammable, multifunctional manipulator designed to move materials, parts, or specialized devices through variable programmed motions for the performance of a variety task. So these things actually, if you ask me as a definition, I will say something because I am basically from robotics and then mechatronics and then mechanical design related person. But if a computer science faculty members, if we are asking what is the definition of robot, their definition will be different. But as per RIA, Robot Institute of America, this is the definition of robot. So these are simple how to make MIT Schismat, and so many robots are came. Just I want to put it for your reference. And the ideal task, you know that it can be used in dangerous and then boring, and then high precision or speed. So these kind of things we can do this. So the tasks are different level. One is dangerous, boring, and high precision or speed. Okay. So generally they will call it as 3D: dangerous, dull, and difficult. Here I am giving some other terms. That's it. So robotic terminology. So I think most of the professors, those who are teaching robotics, they knew. So one is articulated, another one is end effector, third one is degrees of freedom, and then robot, and then robotics, and finally telerobotics. So articulated jointed arm, that is robot means if the robot is having more number of arms. For example, we are having 2 arms. So if the robot is having more than 2 arms, those kind of robots we are calling as jointed arms. So anyway, later on we will see some of the examples in that. Next one is end effector. So it's similar to our hand. In the wrist, we are having a few fingers. Okay, so the device at the end of the robot arm that is used to grasp or engage the objects, that is called end effector. Then degrees of freedom, each plane in which a robot can maneuver. This is actually based on robotics. So if you are asking any mechanical engineer, they will say that number of independent motion of a system is called degrees of freedom. Then next one is robot. It's a mechanical device that performs human task either automatically or remote control. And robotics, study and application of robot technology. And the last one, telerobotics, the robot that is operated remotely. Next one, robot anatomy. Any queries till now, professors? If you have, you can ask me. Otherwise, I will continue. Any specific queries, professors? Okay. Shall I proceed further?
Sir, yes, sir. Yes, sir.
Yeah. Thank you, professor. So the next one, robot anatomy. So it's very important because kinematics is very important. So it's concerned with the physical construction of the body, arm, and wrist. Okay. So most of the robots, if you see that industrial robots that are mounted on base, which is fastened with floor. These things we have come across in various industries. Next one, the body of the robot is attached to the base, you know that. And then the arm assembly is attached to the body. Then the end of the arm is the wrist. Okay, this is the geometrical schematic representation of robot anatomy. And one more thing is the wrist consists of number of components that allow it to be oriented in a variety of positions. So the thing is here the end of the arm and the wrist is very important, and then the wrist, what it is doing is important. And as like our human hand, the relative movements between the various components are provided by a series of joints. The body, arm, and wrist, sometimes called as manipulator. Okay. The technical name for the robot hand is end effector, and the end effector is not considered as robot anatomy. Please take a note of it. So whenever we are purchasing any kind of robot, so if you come across, the industry will say that the end effector will not come in robot anatomy. Even workspace also, they will plot and give according to the body and arm of the robot, not with the wrist. And one more important thing is the arm and body joints of the manipulator are used to position the end effector. That is very important. Okay, and only the wrist will use for orienting the objects. these are the things which are important in geometrical point of view. That is, it is having joint, link, and then main important thing is the relative motions are achieved by joints and the links are rigid members, similar to our hand. Okay, that's the thing. Fine, then most of the robots are 6 degrees of freedom, you know that. And then, as I said, body and arm are used for positioning of objects in the work volume. Wrist assembly is for orientation of objects. Okay, now we will come to our kinematics. So before going to kinematics, I want to explain about manipulator joints, and then we will do the remaining things. So manipulator joints, so it is having different varieties. We will see one by one so that you will understand much better. So the first one is translation motion. It is having two joints, that is linear joint, another one is orthogonal joint. So if you see the first sketch, there is an input link and then output link. The joint motion will be linear. So these kind of joints are called linear joint. The type is L. We will say that joint notation scheme, instead of linear joint, we will make it as L. Similarly, we will have orthogonal joint. That is, there will be an input link and there will be an output link. Okay. So always the output link will have an offset of 90 degree to the input link. Okay. So these kind of joints we will call it as orthogonal joint. And sometimes the linear joint we can put it as a prismatic joint also. Next one is rotary motions. So you are having a rotational joint, twisting joint, and revolving joint. So rotational joint, the axis of rotation is perpendicular to the axis of the two connecting links. Then it is rotational joint. Example, you can say, I think all our professors, so we definitely come across the mini drafter. Okay, the mini drafter, you can say that it will move only on a plane. So those kind of joints are called rotational joint. Next one is twisting joint. So if you are standing in a floor and then we are rotating by only on a plane, both those kind of joint and output link axis will be same. Rotation and with respect to twisting, the output link will. So if you are both the input link and output link axis will be in a same line. That is twisting joint. The third one is a revolving joint. So the input link is parallel to the axis of rotation and the output link is perpendicular to the axis of the rotation. So simple example, you can take that our fan actually with one blade you can consider. So there is a rod is there and then one blade is there, how it will rotate. That is a revolving joint. Okay. Any doubt in this, professors, so that we will be very clear on this? Any doubt? No doubt. So I can proceed further, I think so. So now the important thing is joint notation scheme. As I said that we are using the joint symbols L, O, R, T, V. So these are the things. So linear joint, orthogonal joint, and rotational joint, twisting joint, and then revolving joint. So,
hello.
Yes, professor. Any doubt?
Sir.
Yeah. Okay, fine then. The thing is, is it clear? Professors, any doubt? I'm getting some voice.
No, sir.
Okay, fine then.
Ajal?
Yeah, okay, fine then. Okay.
Ajal? Participants are muted or not?
Okay, fine, professor. No problem, no problem. Okay. So the thing is, actually, the very important thing I want to discuss here in particular slide is the body and arm assembly and the wrist assembly. Okay, always they will separate with the colon. Okay, whenever you are buying a robot or if you come across any kind of the research paper, so you can understand that it is TLR colon TR means totally the total robot is having 5 degrees of freedom. The TLR is 3 degrees of freedom and TR is 2 degrees of freedom. So body and arm is having 3 degrees of freedom and wrist is having 2 degrees of freedom. That is the meaning of that. So most of the journal papers or research papers, you can come across these kind of joint symbols L, O, R, T, V. Okay, that's the thing. And next one is the examples. So you can see TRT colon R. So this is the way they will represent in the joint notation scheme. No need to draw in 3-dimensional and all. So if you are drawing these symbols and then you are marking it, then easily we can understand how the robot is designated. So T twisting joint, R rotational joint, T again twisting joint, and R is rotational joint. I'm talking about the first sketch. So it is having 3 degrees of freedom in the body and arm, and 1 degree of freedom in the wrist. Okay. Similarly, you are having B. It is having totally 5 degrees of freedom. TVR, that is related to body and arm. TR is related to wrist. Similarly, the last one, you are having 3 degrees of freedom. That is RR, rotational in body and arm, and the twisting is related to wrist. Okay. Then robot classifications, it will take time. So just I want to go through fast. Arm geometry. Based on arm geometry, you are having different types. Degrees of freedom, you are having different types. Power source, you are having different types. And then type of motion, we are having different types in robots. And then path control also, we are having different types. Okay. And the intelligent level also, we are having robots in 2 categories, low technology and high technology. Okay, then arm geometry, you know that it is having rectangular coordinated. So this is a sample sketch of the rectangular coordinated. So if you see the sketch, you will understand that it is having 3 linear movement. Okay, so if you consider Z, if it is L, then your y-axis and z-axis will be orthogonal joints. Okay, so Z will be linear, Y will be orthogonal, and X will be orthogonal. So these kind of robots are called linear orthogonal robot, otherwise LOO joint robot. Okay, so example, you can see the crane. Okay, so this is the way, and you know the front view, and then top view, it's given clearly the work envelope and cuboid structure. This is the example. As I said, LOO, linear joint, orthogonal joint, and orthogonal joint. Okay, why I am saying all these things is when we are doing kinematic analysis, the representation will be easy. Okay, that's the thing. And then next one is cylindrical coordinate. So if you see the sketch, you have one rotation is there, and then you are having 2 joints. One is linear, another one is orthogonal. So one rotation is playing a role. So this is the example of cylindrical coordinated robot. So it is having, you know, that the swing, the view is there, and the elevation is there. So this kind of robots will give a cylindrical workspace. Okay. So as I said that it is having twisting, one twisting, that is T, and then L is linear, and then O is orthogonal. This is the notation of this particular robot. Okay, and then last one, spherical coordinated. So this thing, the work envelope, it will give you a spherical volume or volume. So it is having two rotational joints, that is theta and beta you are having, and then you are having one linear joint. If you are coming to this particular thing, it is known as TRL, that is twisting, and then rotational, and then linear joint. Okay, so these kind of things you can have in the polar coordinate robot, we will call it as. So these are general different classifications of robot that are used in the industry. Okay. The very important one I want to discuss is SCARA robot. Okay, this is the robot first that we have used in the industry for picking holes and then pick and place application. So we'll call it as selectively compliant assembly robot arm. The notation is VRO. So V, you know that it is a revolving joint, R is rotational, and O is orthogonal joint. So if you see the sketch, you can understand now that is this particular, 1 minute. So this particular thing is, you can say this is the axis, and then this is the axis of this. So as I said that it will look like fan. Okay, it will rotate like this. Okay, so that is a revolving joint, and rotational, you know that it's a plane only. This axis and this axis, it will move like this. That is a rotational joint, that is a revolving joint. And this one, you know that with this link, it is having a 90-degree offset, so it is orthogonal joint. So this is the way we can define the configuration of robot. Okay. Further, as I said that we use it in industry, this one only, so you can proceed further. Then next important thing in specification of a robot means wherever we are going. So we will purchase, suppose for a college, if you want to purchase any kind of a robot, please make a note of these parameters. So these parameters are important. So one is load capacity, how much it is going to carry, we can ask. So with end effector, without end effector, how much it is. Then mobility. So you have to check the mobility that is related to the degrees of freedom, and then workspace, how much you want to cover, and then agility. So how fast it is moving, and the velocity and other things. And then finally, precision and repeatability, how precise it is, and how many times it will achieve the same point. All those things you have to consider. The last one is where you want to use, whether you want to use it in a teaching purpose, or you want to use it in a food factory, or you want to use it in an industry. According to that, we have to select the robot. It's a general criteria. So all these things I have already explained. These are general about how you have to select the robot and what are the specifications are important. Okay, fine then. And the measures of performance, you know that it is based on work volume. Different types of work volumes are there according to the robot structure. And then speed and acceleration, it is the second one. So how much speed it is acting, and how much acceleration you can give to that particular robot when it is carrying a load. All those things are the important parameter for measure the performance of robot. And then final one, resolution, obviously. So it's a smallest step the robot can take. Okay, that's the thing in resolution. As professors, all of you must have come across all these definitions. Okay, if you are teaching a robots. If not, please, these are the things are important for to measure the performance of a robot. That is working volume, speed and acceleration, and then resolution. Okay, the thing is continuous, that is accuracy, and then repeatability, as we discussed. So accuracy, you know that the difference between the actual position of the robot and the programmed position. And repeatability is, will the robot always return to the same point under the same control conditions. So these two are very important. Okay, levels of safety. You are having 3 levels. And according to that, you can design the sensor system. Perimeter, penetration detection. It's better I can go to the sketch and then I can explain. So this is the thing actually. Based on the robot, we can have actually. So if the robot is here, so this is the robot. So we are having different level. The level 2 is here, level 3 is here. And then you can see the level 1 is here. Okay. So level 1 is the workstation perimeter. So once you are entering it in the perimeter, that is level 1. And then level 2 is within the workstation, that is level 2. And the level 3 is the adjacent to the robot arm. According to that, different levels of safeties are there. Okay. So these are general in robotics design. So I want to convey to you. Okay, fine. Grippers, you know that we are having different grippers, mechanical, vacuum, and then adaptive grippers and special purpose grippers. Anyway, my topic is fit to the kinematics. So after explaining this brief intro, I will move to the kinematics. Okay, and sensors and transducers. So if you see that we are using these many sensors in robotics. So accelerometer, gyro, metal detector, gas sensor, all those things from starting to end, we are having n number of sensors which are used in robotics. Okay, so these are simple examples and where we can use the sensor. For example, resistive sensor, you can use it in bench sensor, potentiometer, resistive photo, and tactile sensors, infrared sensors, all those things. Okay, so application, you can ask that where I can use this sensor. So measure bend of a joint, you can use a sensor. Wall following, you can use the sensor, and the weight sensor, you can use it where the load is acting a vital role. Types of actuators: electric motor, hydraulic actuators, and pneumatic actuators. I think most of you know that servo motor, stepper motor, and DC motor we are using it. Okay, and electric actuators we are having. So 3 actuators: hydraulic, pneumatic, and electric actuator. According to the load condition, we will select any one of this. Okay, and also according to the condition also. And recently there are some developments in the sleep memory actuators. So currently research are going on this particular area. Okay, with this, any queries till then, so that I can move to the kinematic analysis.
Yes, yes, dear participants, please raise your hand so that I can mute yourself. If anyone has having any query, please raise your hands so that I can mute yourself. Sorry, unmute yourself. Anyone is having query? Piyush Kumar Singh, Pawani. Piyush. Yes, I have allowed Mr. Piyush Kumar Singh. Would you like to say something or you are having any query? Mr. Piyush?
Okay, Professor, so that I can start, I think
If
so, isn't it?
any participant, if any participant is having any query, please raise your hand so that I can mute you. Unmute you. So, sir, you can start. Professor Selva Kumar, you can.
Thank you, Professor. Okay. So next we are moving to the kinematic analysis. Okay. So we have come across various types of robots, and we have come across what are the basic principles to be followed in robot design, and then what are the structures are available, and what are the joint notation schemes. All these things we have come across. Now we are moving to the kinematic analysis. The kinematic analysis, when I'm talking about that, it's deal with the study of the relative motion existing between the linkages or bodies. The people, those who are working in this field, or those who want to work, you can listen this so that it will be easy for you to work on these areas, and then you can produce a number of research papers in this. So as like said, that it is a study of the relative motion existing between the linkages or bodies. And there are two types of kinematics. One is direct kinematics and inverse kinematics. For better understanding, I will explain with the sketch later. The direct kinematics means, so I am going to mapping from a joint space to Cartesian space is referred to as direct kinematics or forward kinematics. So now you want to know that what is joint space, what is Cartesian space. So the thing is, if I'm having a robot, anyway, I explain in the next slide. Anyway, I can explain here also. So if I'm having a small two link robot, so each thing will have some angle with respect to the horizontal. For example, I'm saying theta 1 and theta 2 simply. Okay. And link 1 will have some angle and link 2 will have some angle. At the same time, I know the endpoint also. For example, if it is a planar manipulator, it will have x and y. So mapping from joint space means that is theta 1 and theta 2 to Cartesian space, that is x and y is the Cartesian space. Okay. And theta 1 and theta 2 are a joint space. Okay. So if I am mapping from joint space to Cartesian space, it's referred to as direct kinematics or forward kinematics. Okay, that is the thing I want to convey to you. And then, so if the joint variables are given, so as like I said, theta 1 and theta 2 are given, we can find the end effector position, that is x comma y. Okay, here I put MP, that is not related to the topic, but it is generally it is on the end point x and y we can calculate. Okay, so the forward transformation finds the corresponding Cartesian configuration to a given set of joint angles. Okay, so now I think in this you can understand much better. The inverse kinematics is quite opposite. That is, we are mapping from Cartesian space to joint space. It's referred to as inverse or reverse or backward kinematics. So in this, the position and orientation of the end effectors are given. That means you know x, y, and then the link lengths L1 and L2, and the joint angles we have to find. So these are the two kinematics what we are following in robotics. Okay, so the inverse kinematics is more interesting from the robot's control point of view. Okay, that is since it's most applications takes are tasks are specified in Cartesian coordinates. So, and inverse kinematics is computed to arrive at the joint coordinates to be used by lower level joint controllers. So inverse kinematics only, the those who are working in this particular area quite interested on that. Okay, that's the thing. Okay, fine. some example I can explain now. So hope you will listen so that if you have any queries, you can stop me in between. So forward kinematics, as I said that where the robot hand is. Okay, if all joint variables are known, that means if I know theta 1, if I know theta 2, here it is theta 1 is shoulder and theta 2 is elbow. Okay, and then you know that the end position, that is x and y. Okay, and you have to know L2 and L1. Okay, and inverse kinematics is to calculate what each joint variables. There is here I am very particular about theta 1 is how much, theta 2 is how much. Okay, but in the forward kinematics I am very particular about what is the x value, what is the y value. Okay, so as I said, it is in the origin. This is for example theta shoulder, and you know that the entire thing you can take it as theta elbow. Okay, so when we are calculating this mathematical relations, so I'll go with the next one so that you will understand much better about what I am talking now. So how to calculate these things? Okay, why we are doing this? So I have explained in this slide. So in order to develop a scheme of controlling the motion of a manipulator, it is necessary to develop techniques of corresponding or representing the position of the arm at points of in time. Okay, so you have to say that where the robot manipulator is there in order to control it. Okay, that is the main reason we are going for kinematics. So robot manipulator can be divided into two basic elements, that is as like I said, one is joint, another one is links. Okay, and we know that links are assumed as a rigid structure, okay, that connect the joints, and this is the representation. So with this maybe I can explain you with this so that you can understand the kinematics easily. So consider that there is a RR manipulator. So this joint is a revolute or rotational. Okay, this joint is also rotational. Okay, that's only we are calling this as R and this as R. So this kind of manipulator we are calling it as RR manipulator. That's only I have given here. The position of the end of the arm may be represented in a ways. So here in this sketch, based on theta 1 and theta 2, we can represent the position of this x and y. Okay, and then based on the input parameter of theta 1 and theta 2, we can represent in terms of px and py. Okay, that is x comma y. Two ways are there, as like I said, forward kinematics and inverse kinematics. We will see one by one. Any queries, professor, so that I can go slow? Any queries till now? No queries?
Yes, sir.
Oh.
One query from, please unmute yourself. Yes, please unmute.
Sir, can you hear me?
Yeah,
Yes,
I'm getting you. Please, yeah.
Sir, actually, when you have mentioned from in the forward kinematics, you have told that you have to take the angle with the horizontal. Is it a compulsion, sir?
No, it's not like that. See here, actually, what I have taken is very good question. Actually, the thing is, if you are taking, then it will give a relative angle. You know, for example, if I am taking this one theta 1, okay, this is the theta 1, and then this is theta 2. But sorry, this is theta 2 and this is theta 1. Okay, so when I am calculating for the entire thing, anyway, I need a reference, right? I need a reference point. Okay, so from this, if I am calculating, automatically it will come what? Theta 1 plus theta 2. Are you getting me?
Yes, sir. Yes, sir.
Yeah, so that is the thing I said, that it's better to go with the axis x and y.
Okay, sir. Thank you.
Okay, anyway, we will solve it one by one. We will solve it so that you will understand much better. So in this, okay, thank you for your question. So we will see now one by one. So first one, I am going with forward transformation. Okay, as like I said that going from joint space to world space is forward. I'll explain one by one so that you will understand much better. Okay, sorry. Yeah. So going from world space to joint spaces, reverse transformation. We will see one by one. Yeah. The position of the end of the arm is given. So I will draw here so that maybe people, those who are interested in kinematics, you will understand. So I am taking from here to here, for example, first link alone I am taking. And then you know here, this is X and this is Y according to that. Okay. So if I want to calculate R1, you know that I want to know the horizontal component. So obviously horizontal is nothing but L1 cos theta. With the, if I am taking this as theta, and the vertical, you know that L1 sin theta. So I'm talking about the point, this point, that is point 1. Okay. So when I am going to write this particular first point location, that is R1, it will be L1 cos theta 1 plus L1 sin theta 1, not plus, sorry, it's comma. Okay. This is the coordinate. Any doubt in this? If I am taking this as theta 1. Any doubt in R1? Okay, hope you don't be there. Similarly, when I am going with this one, R2. Then
no, sir, no doubt.
Yeah, very good. Thank you. When I am going with next one, for example, like this, it is there. Sorry. Hope you can able to see, I think so. Two things are there, this and this. Okay. And if I am taking only this particular, that is, I'm talking about this. If I'm taking only particular this, actually it is having an angle with the L1 link, that is theta 2. But I am taking with reference to this X. Okay, not with the link 1. I am taking with reference to the X. So obviously the total angle with the horizontal will be theta 1 plus theta 2. Okay. So again I am saying that, so I am taking the angle from here to here. So when I am taking from here to here, automatically the total angle will be theta 1 plus theta 2. And when I am calculating that particular thing, my R2 will be, the entire length will be L2 cos theta 1 plus theta 2, comma, L2 sin theta 1 plus theta 2. That's only I have given here. So this is very important while you are calculating the kinematics. So the position you have to clearly say that, okay, the first one is related to the link 1 and the second one is related to the link 2. Okay, so if I want X comma Y, so I know that maybe I can take a word, I think so, so that it will be easy for me to explain. So most of you would have studied, but for others, simply I'm explaining. Okay. So when I want to calculate this is the thing, this point and this point. So I know that this is X and this is Y. And this point is P of X comma Y. So when I want X means, so obviously from here to here I have to calculate. This will be my entire X, this one. I'm talking about this. And when I want Y axis, I have to calculate from here to here. So when I'm writing this, maybe I can take this and then I can increase. So when I am writing, so obviously it will come L1 sin theta 1 plus L2, sorry. So when I'm going with horizontal, so obviously it will come like L1 cos theta 1 plus L2 cos theta 1 plus theta 2. I will get the coordinate of X. When I'm going with Y, obviously I'll get L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So we know that this horizontal distance is L1 cos theta 1, this one, this entire thing. And then you know this horizontal distance is L2 cos theta 1 plus theta 2. And then you know this vertical distance is L1 sine theta 1, and this entire thing from here to here, the vertical distance is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And you know from here to here the vertical distance is L2 sine theta 1 plus theta 2. Oh, sorry. Okay, this is the thing I want to explain in related to X and Y. Okay, this is called forward kinematics or forward transformations. Okay, so any doubt, guys? So that any doubt, professor? So that if it is there, I can explain. Otherwise, I will move it to the next one. We are just 10% of my presentation. Can I proceed further?
Yes.
Yeah. Okay.
Yes,
fine.
sir. Yes, sir.
Yeah. Okay. Thank you. So the next one is once we have done that. Okay. This X. The X L1 cos theta 1 plus L2 cos theta 1 plus theta 2 and Y, all these things we will get it. Okay. This is called representing on arms position in forward transformation of a 2D of freedom. It's an RR manipulator. Okay. If it suppose it is having some other joints, according to that we have to calculate the position. That's the thing. So next one is reverse transformation. This is quite interesting actually. So we have to calculate in reverse transformation, instead of X and Y, we have to calculate theta 1 and theta 2. So coming to that, in this particular configuration, there is the only possibility of the robot arm to reach the position is two possible configurations are there. For example, this RR manipulator wants to reach this particular point means okay, for example, this is the point and this is the RR manipulator sketch, for example. This is R and this is R. So either the manipulator can move like this and then reach this particular point. Otherwise, one more point is the manipulator can move like this and then reach this particular point. There is only two possibilities are there. One is above, another one is below. Only these two possibilities are there to this RR manipulator to reach the point X comma Y. So that is the definition I have given here. Okay. So it's up to you to assume theta 2 as, for example, theta 2 as positive, or you can assume that theta 2 as negative. Okay. So when you are calling with calculating reverse transformation, all these conditions you have to check. Okay. That's the thing. And after this, okay, so now in this case, we are going to use some of the trigonometric identity to solve the problem easily. So you know that 3 and 4 equations are, I want to recollect that. Okay, then only you will understand what is, sorry. Okay, I think we have written in the word, again I want to recollect that. Yeah, these things you have to take to calculate the reverse transformation, that is inverse kinematics. Okay. This particular equations will be used to calculate the reverse transformation 3 and 4. That is X is equal to L1 cos theta 1, L2 cos theta 1 plus theta 2, and L1 cos theta 1 plus L2 sine theta 1 plus theta 2. Because of these things, we are having a formula called cos A plus B and sine A plus B. So we have to use those relations also to solve these equations. Okay. That only I want to convey. And once you are taking that third and fourth equations, yeah, what we are doing is we are simply rewriting. That is, we are expanding the term. We are simply expanding the term, that is X is equal to L1 cos theta 1, L2 cos theta 1 plus theta 2, and L2 sine theta 1 sine theta 2. If you are using this formula, you will get the equation third in the form of 5, and then if you are using the same thing, if you have, you will get the equation 4 in the form of 6. Okay, so once you are squaring it, obviously x square and then y square, and then if you are adding these two, you will get cos theta 2 is equal to x square, y square, L1 square, L2 square, and 2L1, L2. It's very simple. Sine square theta plus cos square theta will become 1, and then you can cancel all the other terms. So you will get cos theta 2. So from this you can calculate what is cos theta. So this is the first calculation in the inverse kinematics or reverse kinematics. or backward kinematics. So many terms are there for reverse kinematics. After this, so once we calculated theta 2, so we have to calculate theta 1 also. That is, so here what we are doing is, again we are assuming the same thing, triangle, so that you will understand much better. So here what I am doing is, or what we are doing is, so we are taking the point, this point, this is 1 and this is 2 and this is 3, for example. So I am taking the point 1 and then point 2 and then point 3, and then I am making a triangle relationship. Okay, that is, this is 1 and this is 2, and then I know what is this angle, theta 2, and then this one I am talking about, and then I knew that what is this angle with horizontal, that is theta 1 here, and then I know that entire angle I am giving a denotation as beta, and this one I am giving as alpha. So all the terms I have given clearly. Okay. So hope you will understand this. So this particular diagram we are taking, again we are using the trigonometric relation. Okay, so here tan alpha, for example, tan alpha is equal to, here I am talking about, so L2 sine theta 2. So you know that where it will come. Okay, I'll understand. I will draw like this, then you will understand much better. So this is your alpha. Okay, so this vertical distance is L2 sine theta 2. Okay, and then that is, I have drawn a line here. Now you will understand, I think so. Okay, this one, this is L2 sine theta 2. I'm not adding theta 1, please try to understand. And then this one, I know very well that it is nothing but L1 plus L2 cos theta 2. So now I am not taking the component with respect to horizontal, along the line of action only I am taking, like this. This is the link one. The same line I am taking, and this is the end point, and then I am joining this with this, and then I am giving this one as alpha. So this one I know L1 sine theta 1, sorry, L1, and this length I knew that it is L2 cos theta 2, and this one is L2 sine theta 2. Okay, so based on that, what we have found out is alpha we got, and then how to calculate theta 1. So obviously I know that this is beta, this is alpha. So if I am substituting beta minus alpha, I will get the value of theta 1. So in this condition, you see the entire thing is beta, and this one is alpha, this is alpha, this is beta. So obviously I will get theta 1. Okay, so with this tan beta I have calculated. So tan beta, you know that. Okay, here I can draw, I think so. Sorry if it is quite confusing one, extremely sorry. But if you are listening, then it will be better. So this is beta. So you know that the entire thing is y. This one is x. So when you are calculating tan beta, it will be y by x. Okay. So then I am using tan a minus b, as I told you that I want theta 1. So I got theta 1 with this relationship. Okay, if you are having any other queries, please you can ask. Otherwise, I think it is 1:10. So shall we wind up or shall we continue, sir?
Sir, you can continue up to 1:30. It's
no, I have some voice. The question I am not getting clearly. That's only. Can I continue?
Yes, sir. Yeah, you can continue to 1:30, sir.
Oh. Okay, okay, sir. Till 1:30 I'm having. Okay. Any queries till now in forward and inverse?
Hello, sir. Hello,
yes, sir. Please. Yes, sir.
Sir, I want to ask that in the first derivation of forward kinematics,
yes, sir,
we have taken the distance from the reference point.
Exactly, sir.
But means angle from reference point.
Exactly. Yep.
But we have not taken the length from the reference point. Means we have to take L1 plus L2, but we have considered only link 2.
In which one, sir? You are saying reverse or in the forward, sir?
Or forward kinematic.
In the forward, 1 minute, sir. I'm coming there. Okay. Here, sir. Yeah, tell me, sir.
Okay, sir. Sir, in R2 calculation.
Okay.
in R2 calculation, you have write L2 cos theta 1 plus theta 2 plus
That is
L2
with
sin
respect.
theta.
Yeah, exactly. That is with respect to link 1, sir.
With respect to 1. But angle is taken from the reference point.
Yeah,
Angle is
exactly.
not taken from link 1.
Yeah, exactly. You're right. That okay. What I am giving is, yeah, very good question actually. Can I explain here, sir, so that you will understand? Is it okay?
Yes.
Yeah. So this one will be better in kinematics and all. So instead of working on PPT, so this will, yeah, very good, sir. The thing is, okay, I want to give R1 and R2 only, sir, not with respect to the origin. The link one I am taking, and then I am saying that this is, this one you know, I think so, sir, L1 cos theta 1. Am I right?
Yes.
And this one I am giving as L1 sin theta 1. Am I right, sir?
Yes, sir.
So here I am giving that R. This is, this is R. I am giving as L1 cos theta 1, comma, L1 sin theta 1.
Sin theta 1.
Any doubts, sir, in this?
No, sir.
Okay, sir. So when I'm coming with the second one only, you are having a doubt. Am I right?
Yes, sir.
Yeah, exactly. No, that one is also same thing only, sir. So now again, I'm taking only the value of this one, as this one is related to this theta 2. Am I right, sir?
Yes, sir.
Now I want to give this R1. Okay. So I know that this will give the slope value of what it will give, L2 sin theta 2. Am I right, sir? This
Yes,
one will
yes,
give L1 cos, sorry, L2 cos theta 2. Am I right?
Yes.
Yeah,
Yes, sir.
cos theta 2. But I want the coordinate should be like this in L2 also. So how will I give, sir, this one? So in this condition, when it is coming to the horizontal, when I am plotting, automatically there I have to add theta 1 plus theta 2.
Theta.
Yeah, that's only. Here what it came is L2 cos theta 1 plus theta 2, and here it came L2 sin theta 1 plus theta 2. Is it clear, sir, now?
Okay, sir.
Okay, fine, sir. Any
Thank
other
you.
doubts? If you have, please ask so that I can move to the next one.
Excuse me, sir.
If you are not having. Any other doubts, sir?
Excuse me, sir.
Okay, fine. So if suppose if you come across other things, so I can move to the next one, very important for the control, because we are talking about control. So how these dynamics kinematics and dynamics are playing a vital role in this. Anyway, afternoon session, our professor will explain about dynamics. So I am going to concentrate only on kinematics. So after this, so if you want to make an accurate control of the manipulator, okay, it requires a precise control. So when you want a precise controls, you have to consider the inertias and then how the forces are acting on that particular manipulator. So I want to give a brief one. Maybe professor will explain in detail. So here in the static analysis, if you consider same RR manipulator, so if you are considering that this RR manipulator is having different forces are acting, that is F1 here minus F2, and here F2 is acting, and then F is acting. This is the free body diagram of that. So if you are balancing the force on each link, how it is acting, then obviously you know that F1 minus F2 will be 0, because we said clearly that it is a balancing force. Okay. Similarly, in this condition, it will be F2 minus F will be equal to 0. Okay. So this is a simple example of how to calculate the forces. Okay. I'm not going to deal in detail with this, because after session our professor is going to take on dynamics. Just I want to give a brief about this. Okay. And similarly, you can, when you are drawing the free body diagram, you can give a representation like this. Okay. This is the thing, and this is the R2, this is the R1. And this is L1 and this is L2. And finally, you should remember always that F1 is equal to F2 and F2 is equal to F. Okay. So this is for two link of force, how to calculate it. Okay. Next one, I'll move to the next one. Okay. This is related to the torque. Okay. So T1 is equal to T2 plus R1 into F, and T2 is equal to R2 into F. You know that these are distance vector. So distance vector multiplied with the force, you will get torque value. Okay, because it is coming in the rotation, we are calling it as torque. If suppose it is a bending, we will call it as bending moment. That's all. So these are the parameters. So T1, you have to multiply T2 plus R1 into cross F. So the matrix also you have to be very clear if it is coming in space, but the two-dimensional it won't affect that much. Okay, and then similarly T1 you can calculate. Simply you can substitute the formula L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and then L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Just now we calculated X and Y, and then you can multiply it with force acting along X and force acting along Y. So whenever there is a cross product is coming, you have to be very clear that the vector product A cross B cross C cross D is AD minus BC. So simply if you are substituting, you will get the torque 1 value and then torque 2 value. Just to brief about what is happening in the torque. So now you will understand why the kinematics is important in designing a manipulator. Okay, so if you are positioning the manipulator clearly with the parameters, and then easily you can multiply it with the forces, you can calculate the torques easily. So these torques where we are going to give as input, yes, we are going to give it to electrical and electronics engineer to find the exact motors what we want. So based on that we are going to tell it. Anyway, you know that factor of safety will come after this, and then you have to select a suitable motor and you have to check first. Don't buy and then if suppose any motor is 10 kgf, they are saying simply don't buy and then make it run. First you check that whether it is giving 10 kgf centimeter or not. Okay, those things are important. So this way only the kinematics is related to any manipulator design or any robotics design. Okay, that's all. So after this, I think you come. Yeah, any doubt? Yes, please.
Mr. Arun is having some doubts. Mr. Arun, please unmute yourself.
I
Mr. Arun?
Yeah, please ask your query, sir.
So please continue, sir.
Oh, okay, fine. So after okay, fine. Yeah, based on that equations, you can get the force relations also, Fx and Fy. Okay, so now you will understand that how the position kinematics will help to calculate the torque and components of forces. Okay, so you can calculate these things, and these parameters you can give us an input to the robot, and then you can control its motion. Okay, that's the thing. So that's only I want to say here. In the starting, this is 2 arms. We are having up to 6 arms. So now I have asked a small question to you. So to measure the forces and torques in robotics application, what we are using? Any idea? So if anyone knows, you can say. Otherwise, we will proceed further. Okay, fine. Okay, fine then, good. It's a sensors actually. Okay, that's the thing. Okay, fine. Next one is gravity. Anyway, our professors will discuss, so I want to skip this in the afternoon one. And now, yeah, this one, because this is a general in design, I want to say to you. The arm can be constructed with as low mass as possible. That is, more of the motor torque will be used to provide forces at the end of the arm. So if you see that in a serial manipulator, we are facing a problem when we are pick and place application after n number of cycles, the position and accuracy is having some problem because of multiple number of times. There is nothing but due to fatigue, we are getting affected. And one more thing is, most of the serial manipulator getting collapsed because of this mass. So you have to consider the proper inertia. You can see that the position also. In the first one, A is saying that minimum inertia is required because you can see that all the joints are close together, links are also close together. The center of gravity will act within the system or with, it is near to the fixed base. Okay, but if you are going for a fully extended condition of the robot, you know that the center of gravity is going to play a major role. As like our serial manipulator or cantilever in structure, it will create a lot of issues. Okay, so that's only when you are designing any kind of manipulator, you have to keep it in mind that as much as low possible moment of inertia, you have to create it. Okay, that's the thing. Don't go for a fully extended condition. Definitely, due to the cantilever structure, the manipulator will not function properly. Maybe you won't get the exact result what you want. Okay, that's all I want to convey from this. Anyway, the term of forces, torques, and the inertia, our professors will explain in the later session. Okay, maybe tomorrow. So these are the different torques, and it's just dynamic forces and torques of the robot. So you're having so many torques, and then centrifugal effect. All those things will play a major role. For all these things, the basics are kinematics. That's the thing I want to say to you. Okay, this one no need. We will move to next one. Okay. Any queries? I will spend with you for 5 minutes. After that, we can start the new one, where we are going to see DH parameters and other things. Any specific queries, professors?
Sir, one question I can ask that can you tell more about some robot repeatability? Means
Robot?
what is robot repeatability?
Repeatability.
Yes, what is robot repeatability
Okay,
and
okay.
how it is
Okay,
maintained?
okay, fine. Okay, fine, sir. The thing is, for example, okay, just 2 minutes I will spend. After that, I can go. So repeatability, same definition only, sir. Actually, it's not related to that. Suppose you want the robot to come, for example. Okay, you are having, for example, I am saying a robot fixed with 3 links. You can consider like this. Okay, 3 links. Okay, and then you are having an end effector here. Okay, and then it has to come. For example, it has to come. And it has to come and take this object, this particular object. It has to come and place, for example, place, I can say. Okay, it has to come and place the object here, but your robot is keep on coming and placing your object here. Are you getting, sir?
Yes, sir, I am listening.
Okay, here only it is coming and placing always. Okay, so how many times the robot is coming and placing the object in the same point? That is called repeatability, sir. It is not related to your exact location. Are we clear, sir?
Yes, sir, yes, sir.
Are you getting, sir? So this is the thing. So this one you can use with the sensors and then proper kinematics. You can achieve it, sir, with all this control. So how many times it is coming to the same position? Yes, sir. Tell me, sir.
There is doubt.
Yes, professor.
What is the difference between accuracy and precision and repeatability?
Yeah, that's all I said. The repeatability, it's related to
Accuracy,
how many times.
Have explained.
Yeah. No, just yeah. Yes, sir. Okay, are you clear with the repeatability, professor?
Yes, sir. Thank you, sir.
Okay. Now the accuracy is actually
some overlap between the accuracy and
repeatability. Okay, fine. The accuracy is how much closer this one to your exact location. How much closer to the exact location. This is called accuracy. Okay, professor, I can explain like this. For example, this is the actual location, exact location the robot has to place. First time maybe it will come and place here, and next time it will come and place here. So these the gaps are nothing but it's related to your accuracy. Sorry, this gap, this A and this B is related to your accuracy. Accuracy is not exact location. What do you want? The precision also related to the same thing. How much precisely it is placing it. Is it okay, professor? Shall we move to the next one? Okay, fine then.
Following. I'm following. No problem.
Yeah, okay.
I'm following, Professor.
Okay, thank you. Thanks a lot, Professor. Okay. So now, actually, very next one is I'm having.
One question.
Okay.
Asked that about the inverse kinetic derivation for.
Your voice is not audible, Professor. Sorry, extremely sorry.
Someone is asking about the inverse kinematics derivation for negative value of theta 1 and theta.
No, no, I'm not audible that much actually. Can we proceed further so that I can ask your question later on? I can answer your question. Is it okay?
Yes.
Yes. Okay. Fine then. So now the robot mechanism. So we are having multiple type of robot mechanisms we are having based on the degrees of freedom. So we have three-dimensional, open loop, and chain mechanism. So anyway, time based on the time permits, I will complete. After that, we will go in detail in that. So you see here it is 4-bar mechanism. The people, I think the people will, other disciplines also will be there. Anyway, so this is why it is called. Yes, Professor. Any doubt?
Yes, sir. Can you suggest me that which torque you are talking about actually, the motor torque or the torque applied by the force of the body?
Very good. Actually, first we are talking about the design of the system, Professor. So we did not consider any major forces. For example, you can consider as a self weight.
Okay, sir.
For the self weight, first you design, Professor. After that, you apply the actual force. How much you want to lift? For example, first you design for self weight of these links. Based on this, okay, you can design, and then you will get the value of torque and force. After that, you are going to introduce a pick and place, for example. Maybe here you will have an end effector, this particular area. So this particular area is going to, for example, lift a load of 2 kg. You apply now you apply a force for different configuration. Maybe the force will be vertical, or the force will be horizontal, or the force will be So which one is the worst? So which one is the worst condition, Professor? Any idea? Professor, any idea? Which one will be the worst condition, Professor? The fully extended condition will be the worst condition.
Yes.
Are you getting, Professor? So fully extended condition, you apply the force of 2 kg, and then calculate the force and torque. After that also, please don't go with the design directly. Please multiply it with factor of safety of minimum 4. Based on my research experience, I am saying. If other professors are going, please follow them. But based on my experience on my design, I went for factor of safety of 4. Then I have bought a motor that is for 10 kg centimeter. Okay, but my robot did not move after that also. So why means there are problems like friction, there are losses in the joints, and there are something called design constraints. So apart from selection of motor, we have to consider all these aspects also, Professor. Okay, this is based on my research experience, nothing else. Okay, that's the thing. So now, after calculating factor of safety, if you are going with that, what is that, 4 times of that actual torque or force, definitely your mechanism will work if it is having proper design aspects of these things, the friction at the joints and the design constraints. All these things you have to check once again. That's the thing I have suggested, Rose. Okay. Okay. Please don't.
Expression.
Yes, Professor.
Then we have to put into the expression.
Exactly, Professor. You should multiply, Professor. That is very important. Okay. Apart from that, based on the placement also we have to, that is where it is working also we have to consider, Professor. For example, my robot is going to work in what is the dirty environment. Then I have to consider about the fluid pressure in and around. Hope you got it, I think so. If suppose it is working in the wind area, I have to consider the wind load also on the structure uniformly. So many parameters are there when you are designing a robot, Professor. That's the thing for real-time application. For example, if you are making a design for your own educational center, that doesn't matter. Just you have to make all these designs, and then pick and place applications we can use it. After that, you can learn it further. That is the thing. Okay, Professor. Any other doubts, Professor? so that I can continue. Okay, fine. So I will move to the next one because I did not start the DH yet. So DH is a very interesting one actually. Okay, this one. So as I said that the second one is some of our professors will have a doubts why he is called it as 4-bar mechanism. So maybe I can recollect engineering mechanics to them. So this is the rigid link. So link 1, link 2, link 3, and then link 4. So it's called a 4-bar mechanism, and this is a closed loop. The figure A is closed loop, and then you can know that the figure B is open loop. So we are now dealing with open loop. If time permits, I will discuss with the parallel mechanism kinematics also, if time permits. Otherwise, I will wind up with open loop mechanism. Let's see. So the major disadvantage of open loop, I told you that because of it is fixed at one end, it is in cantilever in structure. So obviously the links you have to put very bulky. The load, if it is heavy, it tries to bend your joints and then members also. So these are the what is the disadvantages, we can call it as in serial manipulators. Okay, that's the thing. So only if you see that our industrial robots or wherever you see the serial manipulator, you can see the base will be very bulky. After that, the shoulder, elbow, and other up to the wrist, it will be similar to our hand. So our shoulder will be big, elbow will be smaller, and the wrist will be comparatively smaller. So the arrangement also same thing in serial mechanism. Okay, fine then. So another 5 minutes. After that, we will wind up the session. We will move to the break, I think so. So these are general. Because I'm dealing with kinematics, please bear with me because I have to discuss a lot about mathematics. So again, I am recollecting whatever we studied in 10th +1 +2 or like that. Maybe nowadays school kids are studying in 5th and 6th standard. So the how to represent a point in space. So the thing is, you know, that is XYZ. So now I am moving little bit from the 2D to I am moving to 3D now. So the point P can be represented AX, BY, and CZ. So the point can be represented as CX I vector and BY J vector and CZ K vector. Just I want to recollect. After that we can move to the thing. So next one, if suppose it is in a space as I mentioned, so you can give with respect to x-axis how much distance, with respect to y-axis how much distance, and with respect to z-axis how much distance the P point is placed. So with respect to x-axis, so you know that it is given in BY. With respect to y-axis, it's given an AX, and with respect to z-axis, it's given an CZ. So once you are hunting, you can write it like this: AXI, PYJ, and CZK. So after this, you can represent in a simple column matrix like X, Y, Z, and W. W, you know that it's related to the scaling. Okay, if you are putting 1, so it will be all the parameters will be unit. If you are putting 2, whether it may be increment or decrement, it's up to you to put the values in W. Now we are moving to the next one. So how to represent a frame at the origin of a fixed reference frame. Anyway, I will relate all these mathematical relationship in terms of robotics in the later part or in the afternoon session. So generally we will take it as if you are having a frame at the origin, that is, and then you are having a fixed reference frame, we will take it as a two different notation, that is XYZ. Maybe it is related to the fixed frame, and then that NAO, that is related to your moving reference. For example, you can have fixed reference as your shoulder endpoint in your hand, and then ANO is nothing but your wrist endpoint. Okay, like that you can have it. So this one you can write it as normal, orientation, and approach vectors. So there is NX, OX, AX, that is related to the X direction, NY, OY, AY is related to Y direction, and then NZ and OZ and AZ is related to Z direction. So this is the way we have to represent frame at the origin of the reference frame. Okay. So somebody will ask whether we have to put like this only or we can align with the reference frame. Yes, you can align with the reference frame. That is not a problem. But I want to differentiate with what is fixed frame and what is the representation of a new frame I want to give. That's only I have given here. Some of the cases in robotics, the fixed reference axis and the moving reference axis will be same. Okay, so those kind of things, it will have only translation movement only will be there in the robot. Anyway, we'll see in the next classes. Okay, so this is the way you have to represent. So each unit vector is mutually perpendicular. I told you as I. So normal, orientation, and approach vector. Okay, so this is, we will call it as homogeneous transformation matrix. Anyway, we'll see in the later session also. This NX, OX, AX, and NY, OY, AY, and then NZ, OZ, and AZ, all are related to rotation. So these three things we will call it as a rotational matrix. Anyway, I will explain the later part. And PX, PY, PZ is related to the translational vector. Okay, those who already studied, you will know better. But others, you just listen that it's a, okay, one is rotational, another one is related to translational. That's all at present. Okay, remaining things I will explain later. So to mark this, yes, please.
So what is the need of changing the frame of reference?
Exactly.
If we have simple frame of reference, then what is the need of changing them?
Yeah, very good question, sir. Actually, the thing is, minute. Okay. Here, I think I'm having a robot, sir, for example. Okay. Now you please consider it is in XYZ axis, X, Y, and Z. Okay. So my origin is here, sir. For example, all the things are 0, 0, 0. Okay. But when I am making the another robot, when it has to rotate, okay, this point is something like this, sir. 5, 4, 3. I'm talking about this origin, sir. So whether I need X, Y, and Z, yes or no, sir?
Yes, sir.
Yes. So in this case, actually, my robot, this particular axis, I will explain here, sir. Anyway, my origin is, you know that X, Y, Z, for example, I'm saying. But in the moving this particular point axis, it will be different, sir. It may not be like same thing. That is, as we said, that N, maybe O, and maybe A. I'm saying that I'm not saying the exact match. It won't be same, sir. It will have its own orientation. Are you getting, sir?
Yes, sir.
Okay, so that's only I'm saying that, for example, I may not place the same thing in the same origin. It is not necessary, because it may bend like this. At the time, the origin will be this X, and what is that, moving frame axis will be different. Maybe this one will be A, this one will be N, and this one will be A. It depends on what we are giving interest, sir. That one I will explain in the later. Hope you understand that why I'm not taking the same XYZ axis. Got it?
Yes, sir. Yes.
Okay,
yes,
fine.
Thank you.
Okay. So the next one is. So next one is how to represent a rigid body. The same way. So if it is in a space, so you can easily represent as NX, NY, NZ, OX, OY, OZ, and AX, AY, AZ, and PX, PY, PZ. Okay, that's the thing. So as like I said, it's a homogeneous transformation matrix we are going to see in the next class. So there always the transformation matrix must be in square form. So why we are keeping this one as is, it is much easier to calculate the inverse of square matrix to multiply two matrices. So only we are making like this, and the dimensions also should be matched. Okay. Then only we can calculate easily in this. And one more thing I can explain to our professor who asked that why we are not keeping the same reference. Just to think your shoulder and your wrist, professor. So your shoulder joint will have XYZ differently, and your wrist will have its own reference axis different. Okay, that's the thing. Yeah.
MNNIT Jaipur, MNNIT Bhopal.
Next one. Time is up, I think. So I'm getting some thing. Shall we wind up, professor? Shall we start this one in next class?
We will again meet at 3.
Okay, if you have any questions,
we start at, we can start at 3, or will it be okay for you?
Yeah, for me it's okay, sir. Even if you want me to continue, I will continue and then complete.
So please continue.
Okay. So I want Professor to explain. Yep. tell me, Professor, so that shall we proceed, or we will stop here and then we will start in 3 o'clock? I'm not getting your voice. Okay.
Please continue, sir.
Okay. Shall we wind up? It's 1:40 now.
So please continue.
Oh, okay, fine. Okay, some of the professors are quite interested. I'm happy about that. So now we are moving to the pure translation in 3D. And when you are considering pure translation, what are the things you have to consider? I want to just give it, but anyway, you will understand also. Okay, that's the thing. Actually, with this, it will directly give the answer, even when I am explaining that. Okay, here, if you are taking this, you can see that there are 2 axes now. You can see that NOA, that axis, and NOA axis at the points. So both the things, you can see that both the things are having the same value. Okay, now it means that it doesn't have any rotation, because both the axes are lying on the same thing. So this point, from the P point, you can see that it is having only translation. It does not have any rotation. So your equation will become all other things, that is the rotation matrix will become an identity matrix, and the translation value, you can see that it will be dx, dy, and dz. Okay, for better understanding, this one I can explain. That is, it is moving from here to here. There is no change in the parameter of the reference frame. Okay, so it is only translating. So when it is translating from this point to this point, obviously your rotation matrix will become identity matrix. This is rotation matrix. And how to give this value, this d value? So this is in space. So obviously it will have dx, dy, and dz. So these are dx, dy, and dz. That's all. So when you are considering purely translation, then this will be your homogeneous matrix. Okay, always transformation matrix. Hope you understood clearly, I think so. So I will move to the next slide. So the next one is
by taking some numerical value.
Yes, exactly. So for example, if you want, sir, that this particular point is 5, 6, 7. Okay, sir. So if suppose I am taking dx, it doesn't have any value. It will be 0, for example.
So your slides are not visible.
Is it visible, sir, or not? No.
Yes, sir. Now visible.
Oh, okay, sir. So for example, dx, it doesn't have any distance. For example, dy is, suppose it is 9, and if suppose not dz, actually I should not say like that. For example, this value, that is second point value, is 5, 9, 8, for example. So your dx value will be 0, dy value will be 3, and dz value will be 1. Am I correct, sir?
Yes, sir.
Okay, so fine. This is sorry. This is 3, and dz will be 1. So this is the way we have to calculate. So these are basic to make any manipulator design, sir. So when you want, for example, if you want to make some projects with the students for pick and place application, so ask them to analyze what kind of joints they want and what kind of motions the manipulator is going to do. Then easily you can achieve this. So these are basics to design any manipulator related designs. Okay. So the next one is, if I am considering the next one. So if I am considering other forward kinematics thing, for example, Cartesian coordinate robot, cylindrical coordinate robot, and spherical coordinate robot, and articulated coordinate robot, how the forward kinematic equations will play a vital role. Maybe we can see in the next class or next session. Sorry, I keep on saying class because of these online classes, and keep on saying classes. Extremely sorry, professors. Maybe if you have any queries, you can ask so that I can answer your queries. We will have our session sharply, as like our professor said, in the afternoon thing. We are going to discuss about all these things: Cartesian, cylindrical, spherical, and articulated. Any specific queries, please unmute and then you can ask professors.
Excuse me, sir.
Yes, professor.
Like my mic was not working. I have a doubt in like inverse kinematics.
Yeah.
We
Inverse
did the inverse, yeah, for
yeah.
RR robot. Like we
1
derived
minute.
inverse. Yeah.
1 minute, professor. I will come to that particular slide so that you can ask, so that it will be